All right, well, first of all, thank you very much to Katie and Julie for organizing it all. It's really nice to be here. So my name is Julia. I travel the world at the moment with my family. Usually I'm based in Melbourne. And I'm an independent software engineer, but I have worked in a bunch of big and small tech companies, including Square and Google here in Sydney, actually. So today's talk is going to be about building a beginner's programming language with Go. It's going to be a talk in a few layers, starting with the motivation for writing a beginner's programming language, the language that I've written over the last year or so with the help of some very generous friends. And then we'll switch gear to the more technical side of this talk, implementing a parser from scratch only with the standard library, and then kind of honing in on an expression parser according to Pratt's algorithm. So, why build a beginner's programming language in 2023? I've asked a lot of my friends and colleagues the question, how did you get into coding? And I think the answer I got most commonly, especially amongst those in their 30s or older, was basic. So the B in, who knows what the B in basic stands for? Yes. Beginner's all-purpose symbolic instruction code. So you might have some negative things to say about BASIC, but it was targeted at people who didn't know how to code. Personally, I was introduced to programming at high school with Pascal, which also had as explicitly stated design goal to be a teaching language. So both of these languages are now more than 50 years old and are sometimes listed amongst languages going extinct, which I personally think is really sad. So they haven't kind of kept up with, modern practices, Stack Overflow communities, and web-based playgrounds for snippet sharing and interactive documentation and maybe canonical syntax formatting. Thank you, Go. So one of the reasons for building a beginner's programming language is, for me, because I feel like we're really missing one. Another way bigger reason for me personally is my two daughters, who have by now both asked me to please teach them coding. Pressure's on. So we started with block-based coding. You might have seen that, Scratch Junior on the iPad, Scratch on the web, Microsoft's Make code for microcontrollers. It's actually pretty fun and powerful. You can build little interactive stories and even make microcontrollers interact with the real world right from your browser. And you can even build little games. However, there is a certain limitation to these sort of virtual puzzle pieces that you snap together. And it's not so much the language itself, in my opinion, it's more the user interface. After a certain size, it becomes a little bit messy and unwieldy. You don't find your way around. Or, in the words of my older daughter, I don't want to do these babyish puzzle pieces anymore. I want to do the real code. So we tried. And it was actually a little bit heartbreaking, to be honest, to first explain what that funny squiggly thing is, the curly brace, and where she could find it on the keyboard, and then the cryptic error messages and all these other things, that other characters she hadn't seen before, and that white space usually doesn't matter, but sometimes it does. And so it's like one of the things that I think we as a coding community find hard to appreciate, how high this initial cognitive load or cognitive hurdle is for beginners, and especially young beginners. We have all automated and internalized that. But it's really sad because it crowds out a beginner's mental capacity, I think, so they can't really get into what it's all about, namely the sort of algorithmic thinking. Where's the repetition here? Where would I have to place a loop in my code? Where's the thing that I will have to stick in a variable so I can take it out later? There's just no space for that anymore. So I have noted with my kids, like others before, that there seems to be a big gap between block-based coding and conventional programming languages. So I've tried to put something in there. It's a programming language called Eevee, and it's written in Go, and it's been very much inspired by Go. Go's appreciation for simplicity, the thoughtful language specification, and also maybe some bits of its syntax. However, Eevee's syntax is first and foremost minimalist, especially when you get started with coding. There are less special characters and sort of advanced concepts that pretty much any programming language that I know. There are no closures, there are no higher order functions, there are no lambdas, there is no meta-programming, there are no classes, there aren't even custom data types or structs. However, the colorful fun bits are there pretty much from day one. So it's quite easy to create a drawing, I'll show you in a sec. And for that to work, I've used the web as a medium, and like we learned yesterday, we can make Go run on the web with WebAssembly. I've been using the TinyGo compiler because having spent about 2 of the last 3 months in East Africa, I have learned that a web page that has a total weight of 200 kilobytes is a web page that is a lot more likely to load on any network than a web page with 2 megabytes. So there is a factor 10 difference at the moment in the WASM output of TinyGo versus Go. Now, looking at Eevee's syntax real quick. This is a hello world program in Eevee. Like I said earlier, no parentheses, no semicolons, as syntax free as I could manage. Comments start with a double slash, no surprises here. And like I said earlier, graphics are first-class citizens. On the website, this little square is where you draw. It's addressed like a Cartesian number plane, so not inverted like it's often done in computer graphics. We've got the origin in the bottom left, and the extent is 100 by 100. So if you want to draw a line in Eevee, you first set the drawing pen or cursor or turtle in turtle graphics with the move command to here, x coordinate 10, y coordinate 20. And then with the line function, line command, you draw the line here to the center of the canvas. And there's a bunch more graphics functions like for setting styles, the color red here, and the circle shape function that draws a circle for a given radius at the current position. So this is how you draw a pin in Eevee. Eevee is a statically typed language. It's a little bit of a tricky decision, but I thought you kind of have to understand types in coding anyway, so you might as well make them explicit. And also, as I said, I learned with Pascal, and I actually really quite liked the types in the beginning, but I'm not a hardcore static typing person, so I thought about that a long time. There are 3 basic types, num, bool, and string. Num, like JavaScript, is an integer or a floating point number. So the variable declaration is variable name followed by a literal colon and then the type. There is type inference. So here we've got a weather variable of type string with the value sunny. And there are only 2 composite types. We've got arrays, more like a Go slice, and we've got maps, more like JSON objects really. So the keys always have to be strings. The values can be whatever you specify. And there is 1 dynamic type, should be familiar to all the gophers in the room. It's called any, so a variable of type any can take values of any type, like the string or the number here. An if statement starts with the if keyword, ends in the end keyword, has an optional else branch, and an optional repetition of else if branches. There is no case statement. Now loops. I first wanted to do loops like Go, just a single for loop, but I did some serious user acceptance testing with the little users in my home, and it turned out that the for loop is a little bit too dense a concept to get started with. It was easier to kind of lay it out a little bit more explicitly and just have a single condition. So once the while loop was clear, it was easier to translate it to a for loop and back again. So here we're looping over the variable n from 0 to 3 in those 5 lines of code. The same thing expressed as a for loop should be again familiar. However, the range, numeric range statement here also takes an optional start value and a step, a bit like Python. You can for range over arrays, like this Boolean array here with the values true, false, over the keys of a map and the Unicode code points of a string. Function definition starts with the func keyword, the function name, an optional return type, and the parameter list. So this coprime function here returns true if the greatest common divisor of the two parameters is equal to 1. And it's called like so. No parentheses, no comma between the arguments and around them. User interaction is done via event handlers. So this on-key event handler is called every time you press a key, and it just prints out that key, including the unprintable keys like the shift character, hooks straight into JavaScript's eventing system for most parts. Now here we've got a quick little screencast of doing an animation in Eevee. We first move the cursor to the center of the canvas and set the drawing pen to purple. And via the variable r, we draw a circle with radius 30, so big purple circle in the center of the canvas, no surprises here. And then with the onAnimate event handler that hooks straight into JavaScript's request animation frame, we first clear the previous circle, reduce the radius by a fraction, and draw it again. So when we execute this, we get a disappearing circle. Switching gear a little bit to the more technical side of this talk, let's start with the definition, just to make sure everybody's on the same page here. What is a parser? Well, in its essence, a parser is some piece of software that takes a sequential input, like a string, an I/O reader, some text or tokens, and turns it into some kind of structured, often hierarchical output, like a JSON object, or in the case of a programming language, into an abstract syntax tree, AST. But how do we actually get from source code to a program in execution? And where does the parser fit with all of this? So there is obviously many, many ways of doing this, and I have picked the simplest possible way I could find, which is clearly not the most performant one. Maybe this is the slow reference implementation for something that comes later. But you typically have a Lexa component that takes the source code as input and creates the sequential token stream from it. The parser takes these tokens, turns them into the hierarchical abstract syntax tree, and then the evaluator, in the case of Eevee, is a tree walking evaluator, turns this AST into program in execution. So at first I thought the evaluator must be a really complicated thing, but turned out actually its code looks somewhat similar to the parser. So in the following, I've kind of taken the, for me, hardest path through the Eevee code base. So if you can vaguely follow along, you probably can write your own programming language, maybe even a beginner's programming language. So, looking a bit closer at the parser. And the parser in Eevee is a top-down recursive descent parser. And the neat thing about that is that it's very close to the syntax grammar in its structure, and therefore quite easy to understand. So let's have a look at the syntax grammar of Eevee. Again, borrowing from Go, we use sort of a version of Wirt's syntax notation. It's context-free grammar. We have got the pipe for the OR operator here, the square brackets for optionality, and then the curly braces for repetition, 0, 1 or more times. An Eevee program on the top level is a repetition of statements, function definitions, and event handlers. And function definition and event handlers can only exist on the top level. A statement, and this is exhaustive and complete, can be a declaration, an assignment, or a function call statement. It can be one of 3 block statements, an if and while or a for statement, where a block statement consists of further statements. So we already see this recursive nature here, a bit of the syntax grammar. That we'll also see in the parser in a moment. And then there is 2 more control flow terminating statements, return and break. The assignment statement in Eevee starts with an identifier followed by a literal equal sign and the right-hand side expression, where the identifier, as is common in programming languages, starts with a letter or underscore followed by a repetition of letter, underscore, digits. And then the same rule for an identifier is used in the declaration statement with the literal followed by the literal colon and the type. Type may be the literal num, string, bool, any, or an array or map, where array and map are square brackets and curly's followed by type. So again, I want to draw attention to the fact that a type may be an array, and an array must contain a type. So this allows for sort of arbitrarily deeply nested composite structures like the matrix variable up here that is of type two-dimensional number array. An if statement is a block statement and consists of further statement, starting with the if keyword, ending in the end keyword, a repetition 0, 1 or more times of else if branches, and a single optional else branch. So that was a super quick tour through the grammar. Let's turn this into Go code. First, a very quick intuition what tokens are. In this Eevee declaration statement, we have first the identifier token for the answer variable with the literal value answer, followed by a declare token, a number literal token with the literal value 6 string, a star operator token, another number literal token, literal value 9 here, and a comment token with the contents of the comment as its literal value. And finally, the new line token as the statement terminator. As a Go type, token might look something like this. It's a struct with a literal string field that holds these literal values that we just saw, the answer and 6 and 9 and comment contents. And it's got a kind field where the kind is, you know, what I called type before. So the identifier, the declare, the number literal, the star operators, all kinds of operators, all kinds of keywords. Now we're finally ready to look at the parser proper. Stripped down to its bare minimum, in my opinion, a parser typically contains a way of looking at the current token in the token stream, peeking at the next one, and then advancing the token stream. And we're finally getting to the parse methods of the parser. These kind of all respond to the individual rules, more or less, of the syntax grammar, and they each return an AST node. The parse methods recursively call each other, and through that recursive call tree, you build up the abstract syntax tree. So on the top level, parse program returns the root node of the AST, which is of type program. It does that by iterating through the token sequence until it reaches its end, and it keeps on calling parse statement on it. The return statement is again an AST node, and it's collected in a statement slice and then just wrapped in that program type. Now, looking closer at parse statement. Parse statement looks at the first token it encounters, and if it's an if token, it will call parse if statement. If it's a for token, parse for statement, and so on. If it finds an identifier token, it's not right away obvious what kind of statement it's looking at, so it needs to peek at the next token. If it finds an assignment token, an equal sign, it will pass assignment statement, column, pass declaration statement, and so forth. So looking at parse assignment statement, we're finally getting close to the leaves of the AST. We know we're on an identifier token, so we can take the literal value of that out as the variable name. We advance the token stream twice, pass the identifier and the assignment token, and now we can pass the expression as the right-hand side of the assignment, and again return that as the node. So we're finally ready to kind of look at the gnarliest part of this talk, the expression parsing. Why is expression parsing so hard? It's hard because, unlike everything we've seen so far, you can't just simply go from left to right. You have to take operator precedences into account. So as we know with this expression here, we first have to evaluate the products 1 times 2 and 3 times 4 before we can evaluate the sum. I hope we all know. So the operators of higher precedence are closer to the leaves of the tree, so they get evaluated first. Whoop. And the operators of lower precedence are evaluated later, closer to the root. Okay, so this Pratt parsing algorithm, if you reduce it to its essence, is actually not very big, and it fits even on a single slide. However, it's a pretty dense piece of code, in my opinion. So I thought long about it, how best to explain it, and I decided to break it down into 2 components. One that builds a tree fully degenerated to the right, and another one, right for you, another one, a tree fully degenerated to the left. And then eventually we combine these two strategies and switch depending on operator precedence. So these three algorithms and some basic tokenizing in less than 90 lines of Go code in a single main.go file, plus a few imports and flag parsing. I'll give you the link to the repo at the end. So this basic tokenizing that I was talking about is done via a tokens type that wraps a string slice of the actual tokens and a pointer or index to the current token. New tokens creates these tokens from an input string, just splitting it on the space character and completely glossing over any error handling, as you do in presentations, I guess. Tokens has got two methods. The next method for return, so it's a bit like an iterator. It returns the current token and advances the index or pointer. And then there is a done method that returns true if we're at the end of the token stream here. Our first algorithm to create this right degenerated tree, parse right, is a recursive algorithm. We pop off the first operand into the left variable, and if this is the end, we're at the end of the token stream, we return it, we're done. That's the base case of the recursion. If there is more to it, we pop off the next token, the operator token, and recursively call parse right again to build the right subtree. Pop off 2 and plus, right subtree, 3 and times, and then eventually we end up at the base case. And the return values build the tree back up. So I'd like to draw attention to the fact here that we kind of built this tree from the top down. Now its counterpart, the parse left algorithm, is counterintuitively, and at least to me, not just kind of a little rearrangement of what we've just seen. It can actually be expressed as an iterative algorithm. That's, I guess, because you go through the token stream from left to right. And it's also built up from the bottom. So again, we pop off the first token, the first operand into the left variable. If that's the end, we're at the end of the token stream, we return it. If we're not yet at the end, we keep on iterating. We pop off the operator and the right operand as is. And now here's the tricky bit. We build a subtree, an expression out of these, and all of that subtree becomes our new left. And we pop off the next operator, right operand. All of this becomes our next left subtree until we finish the whole tree. So we're finally ready to look at the operator precedence parsing according to Pratt, who's an Australian computer scientist, is born in Melbourne, went to uni here in Sydney, ended up working with Donald Knuth, and in the 70s he published his paper on operator precedence parsing. This parser is still used in some languages today, in Lua, in JS-Lint, I think, and in Eevee. So first we need to model operator precedences. We need a seed precedence that's lower than all other precedences. And then here in this example, we have got 3 precedences: the equality precedence for the equals and not equals operators, the sum precedence for plus and minus operators, and the product precedence for times divided by modulo operators. To look up the precedence of a given operator, we have a map that takes as a key the literal operator strings and returns the precedence for each. And then a little helper function that returns the current precedence, that returns the precedence of the current token. Mostly because otherwise I couldn't make things fit on a slide. This is a Pratt parsing algorithm. If you glance at it from sort of one angle, it looks very much like this left degenerated algorithm that we just saw before, where you have kind of a loop at its center, you pop off the left operand, the operator, and you build left as the subtree of the previous pulled together expression. However, the thing that's different is our right subtree is not just popped off the next right operand, it's actually built via recursion. And all of this, we take operator precedence into account. Now, let's think about an expression that would build a fully left-degenerated tree, like 1 plus 2 plus 3 plus 4. In that case, it's really the topmost call that does all the heavy lifting, and it's really all the loop. It's just this top loop where all the magic happens. So we start with the seed precedence lowest of 0, and so in the top call, we're not yet at the end of the token stream, and we step into the loop because the current precedence of the plus operator is greater than 0. And we get the plus operator off and do our first recursive call to get that next operator off. But because the previous precedence of the previous plus operator is the same one as the current precedence, we don't actually recurse any level steeper. So just kind of pop down to get the right operand and back up again. And that builds this left-degenerated tree. On the other hand, an expression where the operator precedence increases as you move from left to right, like 1 equals to 2 plus 3 times 4. So 3 times 4 first, and then 2 plus, and finally 1 equals. So in this case, we always have the current precedence being higher than the previous one. So every time we step one recursion level lower, and by doing so, we kind of build that right subtree. So, and very quickly, a worked example for a mix of the two, the expression we've seen before, 1 times 2 plus 3 times 4 with the operator precedence, the seed of 0, and then 3 for the times operator, 2 for the plus operator, and then 3 again for the second times operator. And the algorithm from the previous slide just copied over. Let's go through that. We start with the seed precedence of 0, and we pop off the first operand, the number 1, into the left variable. We're not yet at the end of the token stream, and our current precedence of the times operator is greater than the seed precedence. So we step into the loop, we get the operator out, and we recurse one level lower. Again, this time passing in the precedence of the multiplication operator 3. We pop off the next operand into the left variable, the number 2. And because we're not yet at the end of the token stream, but the current precedence, we're here at the plus operator, is not greater than the previous times operator 1. We completely skip that loop. We don't build further towards the right. We return that left variable as is, which becomes the right of the subtree one recursion level higher up, and this whole thing becomes our left subtree. We're looking at the looping condition again. We're not yet at the end of the token stream, and again our current precedence of the still at the plus operator is now greater than the lowest precedence. We recurse after popping off the operator again to build the right subtree. And we get the first operand out, our number 3, and this time again, the current precedence, we're still not at the end of the token stream, the current precedence of the times operator is greater than the previous one of the plus operator. So further building towards the right and stepping one recursion level lower, this time popping off the last operand, the number 4, and we're at the end of the token stream. We return that 4, one recursion level higher up again, still at the end of the token stream. The whole thing becomes our right subtree of the root node. And that's the end of the worked example. So if you want to step through that in your own time, there is a repo on the Eevee org on GitHub, the Pratt parsing repo. I have also built sort of a cut-down version of Eevee called E for the top-down recursive descent parser that was shown in the previous segment of this talk. And then there's all of Eevee, of course. And we've got a Discord community, so if you have any feedback or comments or questions, it'd be really nice to hear from you. So talking of community, this is the point in the talk where I really want to thank the community that has been cheering me on and helping me so far. And first and foremost is my dear friend Cam, who's here in the 3rd row. I thank you very much. He has contributed many, many ideas to Eevee and reviewed every single one of the more than, I think, 220 pull requests, and also taught me some make and awk along the way. It's a difficult journey. So Eevee as a language is relatively complete, or I don't really want to add many more features, I don't think. However, and also, thanks to my friend Jason, who's a graphic designer and donated the graphic design for the website, we have got a pretty neat looking website, I think, with even mobile responsive design and everything. However, the goal for Eevee is to be a lot more than just a beginner's programming language with a neat website. It wants to be something like the Khan Academy for Code, where you come without any prior knowledge and through a very gradual progression, through examples and explanations, you like almost unnoticeably learn how to program, starting with hello world and maybe a red circle in the center of the canvas, and learning about sequential execution and types and operators and variables. Make sure this is really kind of mastered, mastery-based learning. I think that's a very powerful concept. And only then step it up to conditionals and loops, and eventually a big step, I think, in when you learn coding, getting an intuition for abstraction, functions and what a good function definition looks like, or function signature looks like, and composite data types. And all of this would essentially give us enough to learn the founding algorithms of our trade, the searching and the sorting and the binary trees and linked lists and so forth. So we've started on this. There are exercises at least on the GitHub wiki, but you can see that the ambition is plenty big. So if you feel like you can contribute in any way, if you think you can provide some guidance or help out with outreach or sponsorship, it'd be really amazing to hear from you. And that's the end of my talk. Thank you very much.